When you deploy an AI agent in isolation, it looks like magic. But ask that same model to execute a workflow spanning 20 subtasks simultaneously, and you hit an immediate cascading wave of system gridlock. You cannot fix this by writing better prompts. The failure occurring here has nothing to do with the intelligence of the model, and everything to do with how the work is routed. The math is unforgiving. In a multi-agent system, a single user request can fan out into 5, 10, or 20 autonomous agent calls running in parallel. Without strict infrastructure governing those calls, that fan-out guarantees compounding latency. Context windows overflow and hallucinations multiply across the chain until the output becomes entirely unreliable. Building a production-grade multi-agent system requires architecting from first principles. You have to explicitly layer memory management, asynchronous coordination, and fault tolerance to handle thousands of concurrent tasks safely.
Scaling an AI workforce is ultimately an exercise in distributed systems engineering, not artificial intelligence. The most common architectural error is the God agent. This is a single, massive prompt given access to every tool and expected to route, execute, and verify all at once. It accumulates too many capabilities, bottlenecking the entire system. To fix this, we cleanly divide the architecture into strictly scoped specialist agents. A retriever searches data, a coder writes scripts, and a verifier checks outputs. Each has a single, testable responsibility. These specialists must be treated as horizontally scalable, stateless workers. All session context is stored externally, so any instance of a coder agent can pick up any coding task. But if these agents coordinate using standard request-reply communication, they introduce severe latency. Deep, synchronous call chains force the entire system to wait on its slowest node, capping your total throughput and stacking up in a traffic jam. We resolve this by decoupling the interactions via an asynchronous message bus, using infrastructure like Redis Streams or Kafka. Agents publish tasks to the bus and move on. Subscribers pull those tasks when they have compute available. This introduces a strict engineering constraint. If the bus guarantees delivery, it might deliver a message twice. You must build idempotency and task deduplication logic at the consumer level so an agent never executes the same database write twice. Asynchronous coordination maximizes throughput, but it completely shifts the engineering burden away from the LLM and onto strict state management. With the workers deployed, an orchestrator agent acts as the central planner. It ingests the initial user request and defines the execution path for the specialists. For highly uncertain dynamic environments, the orchestrator uses a react loop. It plans one step, acts, observes the result, and then plans the next. It loops until the task is complete. But for predictable task families, like a code review pipeline, dynamic loops are a liability. Here, you mandate static workflow graphs or hierarchical task networks to branch sequentially through predefined subtasks. Whether routing dynamically or statically, planners often succumb to one primary failure mode: over-decomposition. Fracturing a workflow into 20 microagents when 3 would suffice does not increase intelligence. It drastically multiplies your coordination overhead and expands the surface area for failure. Effective task decomposition requires enforcing rigid workflow boundaries wherever possible, eliminating unpredictable agent interactions entirely. As those workflows extend into long-running sessions, you hit the critical bottleneck in the system, the strict token limits of the LLM context window. Relying solely on this single context window guarantees silent truncation. The model hits capacity and drops old data, causing agents to abruptly forget crucial prior decisions. The architectural solution is a 4-tier memory hierarchy, governed by a dedicated memory manager agent that routes data based on relevance and recency. Tier 1 is in-context working memory. Fast but heavily constrained, it holds only the immediate state of the active task and the most recent agent exchanges. Tier 2 is episodic memory. This is a short-term session store holding intermediate results and conversation history for the current chain. Tier 3 is semantic memory. Powered by a vector database, this stores facts and long-term domain logic compressed into embeddings, retrievable instantly via similarity search. Tier 4 is procedural memory. This acts as the permanent catalog of validated agent capabilities and strict tool signatures. To maintain this, you must run a background summarization agent. Its sole job is to continuously compress Tier 2 episodic data into Tier 3 semantic embeddings before the working context ever has a chance to overflow. Memory tiering allows agents to leverage immense historical context without exhausting their finite cognitive bandwidth. With context preserved, agents must execute tasks. But language models cannot affect the external world directly. They must interface through an integration layer. You must treat every external capability, like database queries, live web searches, and external API calls, as a tool as a service, wrapped in rigidly typed schemas so the agent knows exactly what inputs are valid. Because agents are autonomous, you must enforce strict role-based permission scoping at the infrastructure level. A retriever agent is explicitly denied access to code execution. A coder agent is explicitly denied write access to production databases. For safe code generation, you require sandboxed execution. Scripts run inside isolated containers stripped of external network access and heavily restricted by file system quotas. Treating tools as strictly permissioned, sandboxed microservices is the primary defense against an agent accidentally damaging an external system. In an enterprise architecture running 10 or more interdependent agents, failures are not anomalies. They are a statistical guarantee. You have to engineer for them. This requires implementing OpenTelemetry from day one. You assign a persistent trace ID to the root request to map the massive fan-out of subtasks. Distributed tracing correlates the exact LLM request, the specific tool invocation, and the resulting latency, making precise debugging possible across dozens of node hops. You also implement action budgets. Every agent operates with a hard limit on the maximum steps it can take and the maximum tokens it can consume per task. When an agent gets confused and enters an infinite hallucination loop, the orchestrator enforces the budget by hard killing the instance. At the integration layer, you employ a circuit breaker pattern. If an external tool begins failing, the circuit flips open, immediately rerouting tasks away from the degraded service and into a dead letter queue for manual review. Defensive engineering and comprehensive tracing isolate system errors before they can cascade, ensuring partial failures do not bring down the entire network. This is the required architecture: horizontally scaled agents, communicating over asynchronous buses, querying tiered memory, and executing sandbox tools. But deploying this infrastructure is only the first step. Operating and evaluating it continuously is where the actual difficulty lies. Standard single model evaluations are entirely useless here. In a multi-agent system, a minor hallucination at step 1 compounds exponentially across multiple agent hops, rendering the final output unusable.
Production requires measuring the end-to-end task success rate, backed by trace-based regression testing to ensure complex agent interactions lock into expected outcomes. You must monitor for prompt drift. If you optimize an upstream agent's instructions, you inadvertently shift the data distribution that your downstream agents rely upon. True scalability in multi-agent AI requires abandoning the illusion of perfect autonomous reasoning. You achieve reliability only when you fully embrace the rigorous discipline of fault-tolerant systems design.